Hmm. Let's see what's that. Okay. Oh, should be on. Let's wait for the stream to get stable and then we'll resume. Getting some problems with Twitch. Yeah, it's not stable. Hmm. Hmm. Right, waiting again for the connection to stabilize. I have decreased the bit rate, which does not seem to be problematic. Okay, having a drop for some reason as my internet has died. Yeah, jinxed. So my bitrate is good. Hmm. Seems to be fine now. Seems to stabilized. So go. Let us begin with Amazon online assessment questions. Oh, so this is just online and not interviews. Oh, these are all online only. So I'm looking for more for actual interviews. So let's look at those instead. So this is for a new grad Amazon in Seattle. Oh, oh, this is for people that have been asked. It's generic, not really. Okay, so some of the problems that we've done, probably. So let's see if we can solve them today. Let's copy this. And, okay, it says given an array, return indices of two numbers such that they add up to a specific target. You may assume that each input would have exactly one solution only, and you may not use the same element twice. Okay, so yeah, so the straightforward n square solution is checking for every pair. Table meant storing a value against this key, and if you find a value against target minus this key, then you have the answer, else you just store this value. But how do you find the key to those numbers? Oh, you store the key in the index against the value. Hmm. So remember, guys. So how do we try and remember that for two pair, it's going to be hash tables. Let's devise when and where hash tables are used. Let me set up the notepad. See if we can write it down. And, just a minute. Okay, that's ready. And we have our screen. Cool. Okay, so all right. So so you use hash tables when say you have a value and you either need to find the same value or some value that has a relationship with this value. So if you can use the function that can give you this value for some input, then and if you find this value in your set means that these two values are related and these are probably part of your answer. Not your complete answer, but maybe part of your answer. So the key takeaway is that if you need to find the same value or a value that is somehow related to your value, then uh, you use hash maps. Cool. Next up is median of two sorted arrays. I think this is a hard problem. I have not done this question because, yeah, it's a hard problem. There are two sorted arrays. Find the median of the two sorted arrays. Overall time complexity should be O log m plus n, where m and n are the lengths of the two arrays. So for an array of odd size, your uh, median is the center element, and for even it is the two center elements sum by 2. So okay, so let's try and think of a logic that'll work. So let's take a corner case sort of example so that we are able to you know solve with the correct logic instead of just uh, the first thing that comes to our mind. So 3, 6, 9, 12, 15. So for this, the sorted array would be 1, 2, 3, 4, 6, 8, 9, 12, 16, sorry, 15, 16, 32. The median would be 1, 2, 3, 4, 1, 2, 3, 4, 6, 8. Okay. Now, since it's given the time complexity should be log m, and anyway it's given log m plus n, and anyway it's given that the arrays are sorted, you should directly think of binary search and hence a log n sort of solution. So if we merge the two arrays and then find the median, it's going to be om plus n to merge them because we need to iterate over every item in both the arrays. So we can't do that. Um, okay, let's see what else options do we have. So let's say the medium exists, of course, median exists. Mm, and we have the size. We can get the size without in constant time. So we know the total size. So let's find the center of our first array. Say it comes out to be here. So either 4 or 8. Um, and for the other array as well, find the center, and we see if the number of elements, hmm so what we want is essentially m plus n by 2 in the in the in the merged array. But we don't actually have to merge the arrays. Say if we know that at least these elements are on the left of the center or these elements are on the right of the center, then we can find the median, because then we'll know that this is on the left and this is on the right, so which means these are on the center. So we have, say, the first array 1, 2, 4, 8, 16, 32. So we find the center. Let's say center is 4, and for this center is 9. And since 4 is less than 9, we'll know that all the elements before 4 will come up before this 9 will, which means, and since we're talking about both centers, uh, the the length of the array that's going to be uh, up to the point 9 is definitely going to be greater than your like the position of 9 is going to be greater than the center, because you added both the arrays and you took their centers, and now to the left of the centers a lot of elements were added than, is it than more than the right of the center? Let's say greater than or equal to. So which means your answer is to the left of your, to left of 9, and it may be to the right of 4. So let's take another example. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you find the center is 7, and for this 1, 2, 3, 4, 5, oh sorry, the center is 3, and since 3 is less than 7, when you merge them, all the elements uh, to the left of 3 will be added to the left of 7. So your median is on the right of 3 now. Let's say 3 included. So now you can say take this sub array, or maybe these two sub arrays, this one and this one, and calculate their center element. Um, so you move the pointer for the smaller array. Uh, Change the cap for the smaller array, because the smaller array, actually, yeah, the smaller array, no matter if it has the greater elements or if it has both elements, say 1, 2, 8, 10, the other one has 4, 5, 6, 7, say 1, 2, 5, 8. It's a little tricky. Okay. So we know you're using binary search, but we're not able to identify the condition that's going to be used. Okay, there is just one approach given here. Okay, it's a pretty lengthy approach. If we can divide all elements in A and B into two parts with equal lengths, and maximum of the left part is less than the minimum of the right part. Is it for A cross B or AA? Because that's obviously always true. Median is max of left part plus min of right part by 2. Phew, guys, it's a tough one to understand. Let me read it for a minute and see if I can make sense of it myself before I try and explain it to you guys. Holy hell, this is a hard one. Let's see if I can see the code make sense. Oop. Yes, it suggests a video to watch. So it does seem like, hmm, hmm. Okay. So despite this being listed here, it's been mentioned that the trivial solution is very obvious and the complex solution is too complex to be asked. And again, where would this ever be used? So, anyway, the gist of the question, I think maybe the gist of the logic was, if you're given two arrays, um, you split them both into arrays of equal length, um, and if the uh, minimum number in this is less than the sorry the maximum number in this is less than the minimum number in this, then you have your solution somehow. Same for these two pairs. Seems very complicated. By the way, you should follow up. You should set up follow alerts and stuff. Have I not? No, I'm not based in US. I am from India. Um, and I'm not sure if I think I do have follow alerts set up probably. Okay, so well, basically, um, there are a few comments suggesting better explanation of the question than are on LeetCode. Maybe you can try and go through them to at least understand. I will myself obviously go through the solution later on, not on the stream, because it's just about studying it, which is going to take a lot of time. So I'm going to do that later on, and yeah, you are welcome to ask me to discuss it later on a stream if you want. But we'll be skipping that question basically for now. Okay. Um, oops. Hide that, please. Longest palindromic substring. Okay. Given a string, find the longest palindromic substring. So there is. Just don't look at the question, yeah? I mean the answer. Oh, anyway, I've covered it with the iPad, I think. Have you tried interview bit? Yes, I have actually the reason why I am doing lead code right now. So since you're new, I'll let you know what we generally do. We're not generally doing interview questions directly. So we've been on the problem section for about a week now, which is when I started, and we've solved say some 115 questions. Half of them almost medium, half of them hard, easy. So the first few days we did easy questions, so we did quite a few of them, and then we started with medium about 2 days back, I think, and or 3 days back, sorry, we did some of them, and now we're jumping into interview questions. Um, and we're starting with Amazon. Uh, so the reason why I started lead code with streaming was because I do have some experience on interview bit as well. I have about 150 questions solved. Yeah, so you say 16 pages, so yeah, about 150 questions. So I felt like I was ready to start doing more problems and different sort of problems, and I found that lead code was one good source. Um, from feedback from friends and uh, the internet. So yeah, so I'm streaming just so maybe I can help others with problems that they might have. So yeah. All right, so we were on the question of longest palindromic substring. So One option is selecting every possible set in the string, which would come out to be um, 2 to the power n, which is obviously unacceptable. Um, the second solution is what I've actually done. What I've actually written down here is to start at every index in the array, in the string, sorry. So say you have A, B, A, C, B, A, C, A. Start at every index and then between two indices and expand your possible palindrome from there and see how long you can go out. So basically, for A, there's nothing on the left, so you stop there. For B, for between A and B, both A and B are different, so you skip. For B, you expand once, you get AA, same items on both sides. So you set your left and right to A and A, 0 and 2. Then you try and expand since this A can't go left, so this is your current max, just of the size 3. Then your pointer moves between B and A. You expand, B and A don't match. You skip to the A. B and C don't match. You skip to the C. Uh, between A and C, A, C don't match. Skip to C, so on and so forth. You go here, you find CC, then you find AA. This becomes your maximum substring. So now the complexity for this is you have to do it for every index and you have to do it up to the length of n for each index. I mean, n by 2, but yeah, same thing. So for each index, uh, n times, which is n square, and for each item between each index n times, which is n square. So your total complexity turns out to be n square, which is way much more better than 2 to the power n. There's one algorithm that exists to solve this question in ON, but you're not expected to know that as far as I've heard. It's called the Mancher's algorithm, and it's sort of hard. I tried understanding it, but I couldn't. Probably because I was in a hurry trying to understand it. Maybe if I give it time, I mean, you could definitely uh, give it a try if you can understand. It's Mancher's. You'll probably find it by the name or longest palindromic substring if you search on the internet algo. You'll find it. You're not expected to know it, as far as I know. And I mean, in the worst case, if you have not studied it or if you're not able to understand it, and your interviewer asks you if there's any better possible option, you can just suggest that you know of this algorithm, but you don't know the answer. I mean, you don't know it exactly. Okay. So let me show you the code for this as well. So this is basically you have a left pointer and a right pointer, and while mm, just expand middle out, and just get the max. That's all. Simple as that. Okay. Let's move to again a pretty useless question. Not sure if I've done this one. Uh, yeah, but I think I did it on IB is why I have not really done it here. Plus, again, this is a very if-else question. If you see a question on lead code that you see is highly downvoted, I recommend not to even do that question because it's one very unlikely to be asked. Irony is given here. And two, I mean, even if you're not able to solve it, you'll probably be able to solve it. It's mostly if and else. This problem is downvoted so much because the conditions are not clear. Again, maybe just if you see this question, just ask your interviewer for all the corner cases and write the code down. It's going to be really easy. Um, I do have the solution. You can check the solution in the discussions. I've not even written that down because it's really not worth it. Um, yeah, so it's really straightforward as such, but it's really not a question worth spending some time even coding. So integer to Roman and Roman to integer again. Same thing, tedious if else conditions, not worth it, according to me. If you would like to try it out, go ahead, be my guest. Valid parenthesis, we have done this for sure. Um, Fairly simple question. Um, Given these three brackets, determine if the input is these three brackets as as part of the input string, determine whether the input is valid or not. So simple logic is that the bracket that you last opened should be the one that you last close, first close. So so basically last in, first out. That's stacks, right? So simple as that. That question should tell you what approach you should be taking. So basically you push your if it's an opening bracket, you push it in the stack. If it's a closing bracket, if it's same as the top of the stack, then you pop it. Like if it's the closing bracket matching the top of the stack, then you pop it and move ahead. Else you exit. If the stack is not empty by the time you finish iterating, which means there were some open brackets left, again you exit. Otherwise, if your stack's empty and you finished your loop, then just return true. Let me show you the code for the same. So I kept a map to see if to match the element on the top of my stack with my current item, just like a key. So if my open bracket value is equal to the close bracket that I'm on, then we pop. Else if it's not, then means we failed. We found the wrong bracket while iterating over the string. Uh, if it's an open bracket, we push. You can also write if mi exists. I mean, yeah, if map m dot find is not end. Cool. Finishing this list does not mean it's for SD1 firstly, and finishing this does not mean that you are ready for an Amazon interview, definitely. But if you've confidently done all these questions, I would say that you are in a good place to try for interviews and stand a good chance of clearing them. Because you never know what kind of questions you're going to get asked. Anyway, okay. So given k-sorted linked lists, return it as one sorted list. Analyze and describe its complexity. Okay, so we've not done this question. I'm gonna hide the notepad. Okay. Um, hmm. Merge K. So you have an array of root nodes. So straight away, firstly you can think about brute force, and since they're all sorted, so you only need to check compare the first element of each list. So you iterate through your vector and find the minimum, and based on which list item gave you the minimum, you add that node into your final list and move that pointer ahead in the list. So that's a straight for brute force solution. Let's look at the complexity for the same. Um, Now, given that you have to add an element, uh, you have to look at the element to add it, the complexity would be at least O, A plus B plus C plus D, so on, where A, B, C, D are the sizes of each input. But um, let's see what it's actually like. So we compare uh, the first element of all our vectors, that is equal to the so let's write it down in the notepad again, since we are not going to just talk in the air. So firstly, our for loop goes from 0 to the size of the vector. So we need to read each element basically, and and once we successfully do find our element after all the comparisons, we will be moving it forward. So we'll be doing this operation for all elements in, say, our first list, then in our second list, then say our third list, fourth list, and so on. The moving. So for each time this happens, um, we move one node ahead, and we know we have to move the sum of size of all the nodes of all the lists. So our complexity would become sum. Let me tidy that up. So it would become the sum of lengths of or our linked lists times the number of lists. So this part was definitely expected, but this part is the additional component. Uh, when we're doing it for just two lists, say, uh, we move it's not the sum of the lengths into 2, it's sum of the length into 1, but that's probably because it's so maybe the formula is not number of lists, it's number of lists minus 1, so it's 2 minus 1, so that's why it comes out to be okay. So yeah, I think this will be our complexity. Let's write it down and see if we can find a better solution in the discussions forum. Okay, so we start with the while. This while would break when all our nodes are null. So let's make a sorry list node return value is new list node. Let's just keep it at 0. This is a dummy pointer. We'll just add all our elements to this list, and then we will return red dot next. Okay, so we're gonna break when they're all null. So let's keep a flag for it. Bool any not null equals false, and for int I equals 0, I is less than lists dot size I plus plus. So let's write our own min function that checks for null. Min list list node star A, list node star B. We can just use values right now, but if it was actually we won't use values. We'll use this itself to see if both are null or not. If A and B return if A val is less than B val, return A, else return B. If A and not B, um, sorry, else return A. If not A and B, return B, else return null. So auto min L is min list list I and list I plus 1. So it's going to be less than this. And that's why our complexity is number of lists minus 1. Oops, sorry about that again. Didn't move the the notepad away. Okay. Min element, found the min element. Now if min element is not equal to null, then any not null is true. If any not null, if not any not null, we can break, and we'll also need to store the index of the minimum element. Um, so int min index equals 0, and then list min index equal to list min index next. If it's not null, then we also need to add it to our result. So let's keep a reference to this, and instead of, so if it weren't integers, we couldn't just copy the value. So let's do temp next equals the minimum element, and temp equals temp next. And okay, I think this will be fine. Oh, sorry. We are iterating and we are breaking, so no problem. Missing template before bracket. Sorry, what? Okay, it's lists. It's linked lists. Okay. Runtime error. Min index is 0. When did I update min index? I did not. Sorry, my bad. Min index equals I. Oh, sorry. Yeah, that's right. Oh, this is wrong. It's not going to be this. It's going to be this and the last. And let's start with 0, of course, but set lists 0. Okay, why is it giving TLE? Because none of them is ever not null. Why? Because we are not moving them forward. Is that why? Hmm. Where did that even break? Broke here for maybe a empty list. That's fine. No, not for an empty list. 0. Oh, yeah, that's fine. Broke for min index. Why would this ever be null? Hmm. Sorry, we not gonna move this, but this only. Okay, let's see where our exception came. It's here itself. So let's just debug now. Let's put the debugger here. Okay, so it's 1132. So probably gonna have this list updated to 4.5, and temp will have 1.4.5 in it maybe. What is min index? Min index is 2. Uh, lists 0, 0, 0, 1, 2. Okay, I guess it's gonna break. Debug. Min index is 2. Okay. Found circle in linked list. Oh, what? Temp. Oh, we have to do this later, not now. Okay. Hmm, that's fine. Let's debug now again and see. Okay, our temp is 134, not a problem. Min index is 2. Oh, it's not I. Huh. It's the index of this in our list. So how do we save this index? So we can just check if and min element is equal to lists I. Only then do we update the min index. Cool. We got something. We got 1, 1, 4, 5. Not bad. Think it broke somewhere. So let's check. Hmm. So first iteration we have 1, 1, 1, 4, 5. After the first iteration we have this one has been removed. Awesome. And then this one has been removed. Awesome. Then the 2 should get removed. Okay, let's start that again. After 2 ones have been removed. One has been removed. Another one has been removed. Okay. Oh, we are setting it at the wrong place. we need to set it over here. Okay. Right, let's run this again and see what happens. Cool, as expected. Uh, Empty lists are probably not handled. Yeah. If lists dot size is 0, just return. I don't know, man. What do you want? Return red. Just return null. And if they're not null and the items inside them are all null, yeah, that should be handled. Oh, so this is pretty slow, taking a lot of memory and pretty slow. Um, let's see the solutions. So brute force is n log n. Traverse all this, collect the values of the nodes in an array, sort the iterate. Oh, okay. N is the total number of nodes times log n. Hmm. Okay. Compare one by one and then iterate. Kn, k is the number of lists. Almost every selection, k minus 1. There are n nodes. N in creating the new list. O1, it's not hard to apply. In place, connect the selected. Yeah, optimized approach 2 by priority queue. Hmm. By the comparison process by priority queue, you can refer here for more information. N log k instead of nk. Number of lists in comparison, the cost will be reduced to O log k for every pop and insertion to priority queue, but finding the node small value just costs O1 time. Okay, so says this create a queue, create a priority queue for all nodes in lists. If it's not null, then put that value of the queue and the node against it. While the queue is not empty, node queue dot get point dot next is new node, point equal to point dot next, node equal to node dot next is the node in the queue. Yeah. And if node queue dot put node dot value. So what this is doing essentially is for all the items in the list, it puts everything in a priority queue. And then takes everything from the queue and pushes into your new list. Instead of the comparisons that we are doing. And priority queue sort like stays sorted. So just pushing in, inserting in the list is the cost that we bear. So we can separate those two loops basically. Okay, decent solution. Another one is merge lists one by one. Same as I think this pretty much. So you merge the first two, then the merged list with the next one, then the merged list with the next one, and so on. Merge and divide and conquer. pair up k lists and merge each pair. After merging the first pair, k lists are merged into k by 2 lists and with an average of 2n by k length, then so on and so forth till we get the final sorted list. Sort of bucketing. So you merge the first two, the next two, the next two, and then next two and the next two, then the last two. So number of times you up do merging is n by 2, then n by 4, then n by 8, and so on. Merging takes the sum of the length of the nodes. So let's just call it on. So on by 2, on by 2, on by 2, n by 2 times. So how is that? We can merge two sorted lists in on time and total number of node in two lists. Yeah. Log k is the number of lists. Yeah, oh sorry, yeah, so k lists. So number of times you're doing merging is k by 2, then another, then, sorry, number of lists, number of merges you do is k by 2 plus k by 4 plus k by 8. Isn't that so? How's it log 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You're literally doing it 6 times. Feels like this should be onk as well. Hmm. Let me know if you understand why this is the first pairing. K lists are merged into k by 2 lists with an average of 2n by k length. So the time it takes, yeah, so that's k. You're doing merging k times for lists of length that are hmm, okay, a little different. Okay, all right. Okay, decent question, I'd say. Not a great question as well. Um, I think most of the solutions work fine. Uh, the solution I gave was, I think, very straightforward. If the interviewer asks for a better solution, then I think you can give the priority queue solution or the last solution, which was not very intuitive according to me. I mean, because to me itself it looks like the complexity is wrong. I'll try and see, read through it and see if it makes sense to me later on. And then I'll let you know. Okay, Yeah, so Sudoku problem. Uh, Given a Sudoku, tell if it's a valid Sudoku, and you don't have to check if you can possibly solve it, only if each box is numbers only 1 to 9, each row and each column is box numbers only 1 to 9. So, sort of a unique solution is you make three 2D arrays, set them all to zeros, and when you find a number, say uh, you calculate the number as an index, sort of 0 to 9, 0 to 8, and you calculate you calculate k as I by 3 times 3 plus j by 3. And if this number occurs in this row, or if this number occurs in this column, or if this number occurs in this box. So basically this k is the formula for a box. So 9 boxes here. Based on I and j, you will find k. If it's already there in that box, then you return false, else you set that value for those to 1. Try and figure out how this was calculated. You can you can write all the i's and j's here and try to see a pattern between the relationship of I and j, and just number these boxes as 0, 1, 2, 3, 4, 5, 6, 7, 8, and see how you can come up with those numbers using I and j. So you definitely make sense to you'll have to divide by 3, but how do you shift them is the challenge in a way. Yeah. So straightforward. It's not if you even if you don't use this solution, this formulas, you can it'll it will increase the complexity of finding if it's in the quadrant or not. Like you'll have to check uh, every 3 by 3 in that case. So this will save a lot of time in terms of complexity, which I don't think, which I think your interviewer will be expecting. So, I mean, at least you have to go in the direction of saying that we store when you find it in a row. So this is found in X row, you found Y number. In X column, you found Y number, so on. And in X quadrant, you found the number. So you have to tell him that, okay, I'm labeling these as quadrants, and we find some relationship between I and J so that they return the quadrant number while iterating through every element. That is the least that someone would be expecting from you. Okay, let's hide that again. Okay, combination sum. I think I've done this. Hmm. So it says given a set of candidates without duplicates and a target number, find all the combinations in candidates where the candidate number sums to the target. And you can use the same number again. So we've done a huge drawing for the same with a huge explanation. Uh, very early on in our first or second stream, I think. Um, so again, seeing the question says select elements from a set to make another set where when some condition is true, your set is a part of the answer. So in general, making a set from a set is backtracking. I mean recursion. So what logic applies here is you can make sets in two ways. Either you can select the element or you cannot select the element. And after selecting the element, you can either move forward and start selecting new elements, or you can continue to select the same element till either you reach your goal or till you overpower your goal. So if you see the answer, it's exactly that. That if the size of our candidate, which is our current path, I think. Mm, no. Oh, yeah. If the size of our candidate is less than the index, I don't think we're ever updating the candidate. Oh, basically uh, when you reach the last element, you exit. If your current sum is greater than the target, then you exit. If it's equal to the target, then whatever path you've walked on till now, whatever elements you've selected as part of your answer, so you push back in your array and return. Because you can't include more numbers in your from your list because it's all positive numbers. Um, and then you either change your index without adding anything to your path, or you add the current element again in your path without changing the index. So the case where you add the current element and change the index also is taken care of when this function is called again from the above line, which takes the same path with the next index. So yeah, this did not have great runtime. Uh, yeah, I've seen that using a for loop has actually been has actually been yeah faster than using just recursion because it iterates over your results in a different way. And again, it's not as heavy on the stack where the function stack where the function status is stored. So yeah, same thing. If you followed the stream, you know how to do this as well for any conditions, whether you are um, whether you're allowed this to use the same element or not, or whether you're not allowed. Sorry, I said the same thing. Whether you're allowed to use the same element or not, or whether there are duplicates in your input as well. Permutations. Again, simple backtracking. Here we've used the for loops to do that. So what I've done is actually a little different. Is that I've added the element to our path and removed that number from the list and used the remaining array to um, to, yeah, to create the remaining path. But a better way, which I read through the solutions back when I was doing this, is instead of erasing, since erasing is actually an ON operation, where n is the position of your number. For large list, this could go very poorly. So just swap that number. Sorry. So just since you've already included that item, you can just move forward with the rest of the array. And when you're done using that element and you want to use some other element, you swap your current element with the one you want to use next. So that way it'll go behind in the list. For example, you were on 1 and you have 1, 2, 3, and you want to start with 2. So you increment your index to 2 and you swap. You're selecting 2 right now, but you swap 1 and 2. Let me show you the exact code that I am sure will make a lot more sense. Not sure which one it is. I don't think this is the one. Okay, anyway, let's just look at this one. Yeah, so basically if you're at the end, you push the result. Else, so say you started from 1, now you are at 2, but your beginning was 1, of course. So you swap 1 and 2, and what is num? Yeah, so you're basically just updating your list itself. You swap 1 and 2, so now it's 2, 1, 3. Now now begin becomes 2. For the second and third element, the same thing is done. So initially you swap 1 with 1, and then you swap 1 with 3. So you get the two lists, 2, 1, 3 and 2, 3, 1. And you swap them back when you have to start again at some other element. So when you start with 3, it'll come back to 1, 2, 3. Then you swap 3 and 1. Then do it for 2, 1. So it becomes 3, 2, 1 and then 3, 1, 2. And then that's it. You have your result. You should look at permutations too as well. I'm not sure if it's going to be here. Yeah, that will blow your mind, honestly. Um, or was it some other question that blew my mind? Maybe it was combinations 3. There are 5 problems, permutation 1 and 2 and combination 1, 2 and 3. I'm not sure if there's a permutation 3 since I've not reached there. You should definitely try those questions and really understand them well so that you'll uh, better able to solve them. Okay. Yeah, so given a collection of intervals, merge overlapping intervals. So there's just 2 conditions. You can do this in place or have some extra space to store the merged intervals. Basically, if these two overlap, as in this is less than this, then your node becomes 1, 6. And if these two overlap, which means this, the first node is greater than this, which means this becomes a subset of this altogether, since this is sorted. So this will always come after 1 and this will come before this, so it's merged. So you can just remove this and update this as, I mean, not change anything essentially. So either you update this with this based on these two comparisons, or you remove this by comparing these two. Else your list remains the same, as you don't need to modify anything. So the way I did it was keep a stack to keep the last two values. So I kept these two values in, and if this was greater than the next element's first node but less than this, so basically if this is if this was less than this, then if this was greater than this, then you merge these and make it 1, 6. Else you just remove this, or basically move your pointer ahead. You can just ignore this and keep this in your stack. So whatever's in your stack is your final answer. And then you compare this with your stack, then this with your stack, however it ends, and you get your final answer. Or you can, or the other answer that I told you about, you can modify it in place by removing some elements or just pushing the final answer in your list directly without using the stack, and then comparing with your list's values instead of stack. It's the same thing essentially. Or if you want to do it in place. Okay. Rotate list. Hmm. Ah, the horrors. The horrors of so many ifs, so many conditions. So basically, rotate a list to the right by k places. So firstly, you find the length of the list, because if k is greater than length, then you need to do it length percent k percent length times. So you find the length, then if the length is same as k, which means you don't need to rotate it at all, so just return the answer. Else you find what k actually is. If it is 0, which should not happen ever, um, unless it was 0 as an input, then you can return head as well. Um, then you can just move k times and then keep another point at the start that moves till your pointer that was moved k times point to the last, and then you can just update this section to point here. That's all. That's all that's done. So not a complicated problem really at all. You can try it yourself. It's really, really easy, honestly. It's downvoted mostly because of the corner cases where k is greater than length and k is 0, head is null, stuff like that. Or it's just one item, so on and so forth. Then word search. I've not done this before. Okay, word search. Is it a medium problem? Hmm. Oh, I have done this. Yeah, it's remembered from this diagram. Okay, fairly simple. So the question was, given this board and given this word, find if the word exists. If you can iterate through the board and connect neighboring elements to make the word. So The question was, if this exists, does the remaining problem, can the remaining problem be solved from the remaining set? And since you have to do it for every, you have to check for every item, and I'm not sure how you can, by standard definition of backtracking, understand that this is backtracking. But yeah, so basically, backtracking seems to be something like doing something similar on some other data and getting a similar sort of result with the same logic. So basically, if you could find A, B, C, C, E, D at the first element, can you find B, C, C, E, D at the second element? Yeah, that's the same problem. If you'd already asked, what can you find B, C, C, E, D in the first place? Yeah, so it's the same problem. The only thing that you have to take care of is setting the board element that you find as blank so that it's not looked again, and then resetting it once you are done with checking that particular path. And just checking if you're at the border, then you can only, if you're not at the border, only then you can move in a particular direction. Yeah, fairly simple again. Validate binary search tree. So it's been about an hour. Yeah, been about an hour since the stream started. Um, my internet seems to be a little unstable. Hmm. Okay, let's take a quick break in say 10-15 minutes, and then we'll resume after some time. Okay, so validate binary tree. So binary tree is a valid binary, a tree is a binary tree if the left child, left, all the nodes in the left tree of a node are less than the value on of that node, and all nodes to the right of a node are greater than that node. So we have one condition, that we need to store the value of the node which we need to compare to. So we need our node's value to to begin with, which is going to be either the greatest or the least value for part of the tree. Um, and then one node should also be, if it's a left node, then it should be um, less than your parent node, and if it's right node, it should be greater than your parent node. So what we do need to check is, as you can see here, if it's a valid tree if the value is, if the current node's value is greater than the minimum value, and it is less than the maximum value. And for each node, we can just set the minimum and the maximum value, as if we're checking for the left node of a left subtree of a node, then the minimum value is it can be anything, because it just needs to be less than something. So the maximum value will be the root node, and to check for the right side, it the minimum value has to be, basically it has to be greater than your root node. So the minimum value becomes the root node, and the maximum value is whatever the maximum value has been till now. Yeah, that's it. So just recursively check it for every node. Remember, you can't just check it with the previous node, because the previous node, yeah, it might be correct in in order with the previous node. So say 2 has a left child 1 and the 1 has a right child of 3. So 1 is less than 2, that flow is correct, and 3 is greater than 1 because it's on the right side, should be greater. That's true, but 3 is on the left side of 2, not this example. 3 is on the left side of 2, but is still greater, so which means it's not valid. So you need to check it with the parent, you know, which was the last worst case or best case parent that holds your maximum or minimum value. Yeah. Okay. Same tree, symmetric tree. Very, very, very simple. Basically, if both nodes are null, return true. And if both are non-null and both have the same value and their lefts are the same tree and their rights are the same tree, then return true. Else return false, which means either of them are null in the middle, then you're going wrong somewhere. Pretty straightforward, really nothing. Once you've done a few questions on trees, this will feel like, you know, as easy as breathing. A symmetric tree, now this is actually very similar to same tree, if you can wrap your mind around it. So basically what we're doing is if the left tree and the right tree are same, are mirrors, then we're good. So how do we check that? Is we pass two nodes each time, and for each node we pass the opposite node. So for the left node we pass, say, if the left one, then for the right we pass the right. If for the left we pass the right, then for the right we pass the left. So we check, is left of left same as right of right, and is right of left same as left of right. And of course, if the values of those two nodes that we're checking right now are also the same. You can see the code, the structure is the same as is same, except for checking two different trees. We're checking the same tree, but opposite nodes. So you can look at this question as also another question. Are two trees mirror of each other? So that'll be the exact same code, except here you'll be passing the root of the two trees. Binary tree level order traverse. Again, so if you are comfortable with BFS and DFS, you can solve most tree questions. Obviously, the complex ones have something different altogether, so you need to solve them differently. But yeah, so basically, this says return the level order traversal from the root to the leaf. So basically, we have to return each uh, all the nodes at each height. So how BFS works is you take a node, store its children in your list, and then you do whatever you did for your node for this list. Now for each node in this list, you store its children, and then you do whatever you want, and then do the same operation for the children. So that's what we have done here. We have taken the parent node, and then for each item in that level, um, we We have saved the values of that level in a list and added that list to our result. And if for any node that was in our queue, if it has left or right node, we push those left or right nodes in our list, in our queue. You see, they're not processed immediately at the same order because the iteration we do is dependent on the size of the list before we started processing the nodes. So you can take a look at this or just go to the discussions forum and copy this answer like I did. I didn't actually write this down because I had already done this many a times. And harder problems like reverse level order traversal as well, so I didn't feel the need to write it. Convert sorted list to binary search tree. Okay, yeah, I think we did this in today's stream itself, and it's uh, absolutely nothing to do. It's just take the middle element, take the left subtree, take the right subtree, set it to the set the limits for your new array to the indices of the left and right, and set your current nodes left and right to the return value of your helper function with those two with the indices. And your helper function will return null for if your start is greater than end, and otherwise it would basically return whatever element needs to be put to the left or the right of a node. You can check the discussion for the solution. I've not even copy pasted it since it's really nothing to even read. I'm probably pretty sure that nobody's gonna ask you this question since it's so basic. Maybe for an entry level SD one, just to check if you know uh, what a binary search tree is, and a height balanced one at that. Because otherwise, if you just need to make a binary search tree of a sorted list, you can just make a slant from the root to the leaf of height n, where n is the number of items, and set every next element to as the right of the previous element. So that's also a valid binary search tree. Okay, populating next right pointers in each node. Okay, this is a good question. Um, I don't want to hurry through this. I said I'll be here for another 10 minutes and they're almost over, so I don't want to rush through this question. Actually, it's a good question based on something that we just talked about some time back. I've done this question before on IB, and I really want you to think about it first. Take out a pen and paper and just see what they're asking. So I'll explain the question if you want. Um, so at each level, you need, if you visualize a tree as shown in the example, you need to set the next pointer's value to whatever is the next node in your tree at that level. So for 1, it's nothing. For 2, at the same level, it has 3. Similarly, for 4, at the same level, it has 5. For 5, it has 6. Although it's part of a different subtree. Uh, so was 2 and 3 in a way. 2 and 3 are say nodes of new trees, root nodes. Then yeah, And so similarly, 5 and 6 are part of different trees. So 5 points to 6, 6 points to 7, and 7 points to null. Similarly, if they had children as well, they would all point to the node next to them on their right. Now there could be nodes that are null. So say if there wasn't a 5 there in the question, your 4 should point to 6. So you need to take care of those conditions as well. So I want you to think about it. I'm not going to be coming back anytime soon. Stream resumes 2 hours from now at 10:30 IST. That is when I would be sharing the solution to this question as well. It's, I think this was one of the first problems that really helped me understand some of the basic concepts of trees really much better, because of which I was actually able to solve some questions that even I thought wasn't going to be able to. For example, I had this interview, and there was a question of trees that was similar to this, but no question. It wasn't a straightforward simply applying an algorithm or a logic. It was of course twisted, but because I had a good hold on this on the algo used here, I was able to solve that question as well with a little bit of tweaking. So I really want you to practice this, code it out, and we will discuss this at 10:30. Thanks for joining. See you guys. Bye.